Hi, I'm Catherine Porter. I'm an independent energy consultant, and in today's video, I'm going to talk about the fire at the North Hyde substation, which took out Heathrow Airport a couple of months ago. We had the final report published this morning, and I'm going to talk about what that report has told us and what we really need to think about in terms of our infrastructure going forward, because although the report's come out with some pretty good recommendations about how we need better coordination between critical infrastructure and service providers to that critical infrastructure, there are some gaps as well in the report which I'd like to highlight. Here we go. So first of all, the report has found that the key piece of equipment at fault was a transformer, which I think we knew. What we didn't really know from the initial report was why it caught fire. So the North Hyde substation was built in 1968, and initially there were just two transformers. They were built in close proximity to each other. Now, in a modern setting, we wouldn't do that, or we would put blast walls between them. But in those days, they had different standards. So these two transformers are very close next to each other. And then some years later, a third transformer was added, but that was at a larger distance. So the fault that occurred was with the one in the middle, and unfortunately, because of the proximity of the one immediately adjacent to it, that also experienced damage. And so we had the middle one caught fire and the adjacent one suffered heat damage. So effectively both of the transformers were put out of service. And so then the whole of the substation would need to rely on the third transformer, but that couldn't start to be used until the fire had been tackled at the substation. They had to de-energise the substation to tackle the fire. And that's why the power was out for such a long time. So why did the transformer catch fire? So first of all, I just want to explain a little bit about what transformers are. We decided, well, just generally back in the end of the 1900s, there was quite a big debate within the nascent industry around how we should set up our electricity systems. And Thomas Edison wanted everything to run on direct current. He had a plan to operate electric motors. At the time, you just didn't have good electric motors that ran on alternating current, so he was very keen on direct current. Nikola Tesla, on the other hand, wanted alternating current. He wasn't so interested in motors. He wanted to transmit electricity over large distances. Now, one of the things that you have with electricity is that when you put current through a wire, then it'll tend to heat up the wire. And over a long distance, that heating effects can cause quite significant losses. So eventually you have to put in so much energy to offset these losses that it becomes completely impractical. However, if you increase the voltage, then that reduces the amount of losses you have. And so it's much easier to transmit electricity over long distances at high voltages. But of course, we don't want high voltages in our homes because that would have safety implications. So we need to then change the voltage from the high voltage for moving electricity up and down the country to low voltage to bringing it into our homes. And we make that voltage change with the use of transformers. And so transformers are basically a piece of equipment that consist of wires wrapped around a metal core. But because these wires have this property of accumulating heat as you put electricity through them, and then you wrap lots of them round a core and they're all close together, this whole thing can become very hot. So it's necessary to cool it. And then, of course, you have to have something that will cool it in a way that doesn't create short circuits between the windings. So it has to be an electrical insulator. Because these transformers tend to be sitting outside, they need to be thermally stable, so they can't freeze in the winter, for example. And also they need to be a fluid, because what you want to be able to do is to pump the material around the windings so that you can take heat away. And so all of these properties are found in oil, and so a type of oil is used as the insulator within these transformers. And so effectively you have a big tank with metal walls, and inside the tank you have the metal cores with the windings around it, and it's all sort of filled up with oil. But the downside of the oil is it's extremely flammable. So, and the other problem that you have is because the metal of the tank conducts electricity, when you're putting the cables through the wall of the tank effectively to reach the windings on the inside and then on the exit side, you need to do it in a way that you don't get cables touching the metal walls of the tank. So you use basically these sleeves, and those sleeves are known as bushings. And unfortunately, the fault occurred with one of these bushings. Moisture was found inside it, and when they after the fire, when they forensically examined the sort of the debris, they discovered evidence of arcing. So arcing is when you lose the electrical insulation properties and electricity will jump over an air gap, and you literally see a spark moving from across the gap. Most commonly you'd see this on trains, around the overhead lines for trains. And so you want to avoid this arcing, particularly in the environment of highly flammable oil. So what they think happened was that moisture got into these sleeves, that created short circuits that caused this arcing to happen, and this ignited the oil within this tank, and the whole thing caught fire. And it was quite a significant fire because the tank was huge. You had very high voltages involved, and it was all old equipment. So that's essentially physically what happened. Now, what the report tells us is, well, first of all, the transformer was built in 1968. In the 1990s, fire suppression equipment was added. Then in 2018, they did the most recent basic maintenance. In 2023, National Grid changed its policy around maintenance, so that whereas before that time they tried to do basic maintenance every 4 years and major maintenance every 11 years, they moved the basic maintenance onto a 5-year cycle and the major maintenance from 11 years to 15 years. Now, even with that, obviously having had the last basic maintenance in 2018, that was overdue, and it should have happened it should have been in 2023, but then it should have been in 2024, and it still hadn't taken place. It had been scheduled a number of times, but for various reasons they kept having to put it off. Another problem that was identified in the report was that in 2022 it was identified that the fire suppression equipment wasn't working. In July 24 it was identified that it still wasn't working. That was another piece of maintenance work that was still outstanding. Now, the opinion of the fire brigade was that this fire suppression equipment probably wouldn't have made a great deal of difference. But I think what this tells us is that within National Grid, there was a culture of around the maintenance scheduling and compliance that was not appropriately cautious from a risk management perspective. They weren't doing the right sort of follow-up around maintenance gaps. And when they were stretching things out, they were trying to extend the lives of some of these older assets as well. Another element that wasn't in the reports, but we know from other information, was this substation had been operating at above its rated capacity. So you're taking very old assets, you're pushing them harder than they were designed to be pushed, you're not maintaining them properly, and then wow, guess what happens? You have it breaks. And so I think this was in fact an accident waiting to happen. Now, the National Grid, the National Energy System Operator report suggests that this is not an isolated incident, that National Grid's wider policy around maintenance is consistent with what they did at this substation. And so they now need to go and look at, well, which other major transformers have got identified problems that are off their maintenance cycle, and that really need to be looked at, particularly where they're end of life and particularly where they are operating above their rated capacity. Now, the other aspect of this is, well, what's the role of the regulator here? Ofgem requires the network operators to produce business plans every 5 years as part of the price control. These are regulated utilities and they're monopolies. So there's only one network provider that does the high voltage transmission system in Britain. that's National Grid PLC, and it is a monopoly. And because it's a monopoly, the amount it's allowed to charge to customers is highly regulated. So the process is that National Grid will submit a business plan to Ofgem, Ofgem will review it, and then decide whether it approves this or not, and whether how much money that National Grid is allowed to spend that it can then recover from consumers through our bills. Now, there's been a huge priority in the last few years to connect renewables. This is obviously an expensive thing to do. Renewables require a lot of grid infrastructure. They have low energy density. You need a lot more cables to connect renewables than you would for conventional generation. And this has been the priority really for grid investment has been around renewables. In the context of a cost of living crisis, that doesn't leave very much money left over for other things. So there's been a little bit of a sort of a chicken and egg here, where Ofgem has criticised National Grid's business plan. It has criticised its approach to assessing asset life. It's criticised its approach to ensuring that assets are adequately maintained. But at the same time, there's been this overriding sense that actually you need to prioritise connecting renewables. And so Ofgem has sort of wanted to have its cake and eat it, doesn't want to charge consumers too much money, wants to have all this investment in connecting renewables, but it just doesn't want stuff to break either. And then network operators are left trying to figure out what the right balance of all of that should be. So I think Ofgem also has some questions to answer here. It's all very well to criticise National Grid in terms of its maintenance plans, but I think it needs to do a bit more than criticise. It needs to be stricter around making sure that critical infrastructure is being adequately maintained, and making sure that people don't take their eye off the ball just because they're trying to do something else, such as connecting renewables. The final thing I'd like to mention is Heathrow itself. Now, we heard a lot at the time from Heathrow executives saying, well, this was an unprecedented incident and, we couldn't possibly have seen it coming. And in the report, it explains that Heathrow thought that the probability of a disruption to the power supplies was so low that it just didn't justify the cost of putting in place mitigations. Now, I challenge that because in 2017, a substation at Atlanta Airport in the United States was affected by a transformer fire. The airport lost power for the best part of a day. It cost them tens of millions of US dollars. And as a consequence of that incident, American airports reevaluated their power resilience. Quite a lot of them put in significant on-site electricity generation. If you look at JFK in New York, they've got a 110 megawatt gas power station on their site that powers all of their needs, and then they actually sell some surplus back to the grid. They're not the only airport in the US that does that. Other airports have gone down a different route where they have automatic switching between grid supply points that mean that they could cut over within minutes. They've got some batteries that would bridge that gap, and they're able to change very quickly between grid supply points, whereas Heathrow had a 10 to 12 hour cutover program, and this was deliberate. This was they planned for that. They said, well, it'll take us 10 to 12 hours. But we've seen from the US that is not necessary for it to take that long. The report actually identifies a couple of different strategies that Heathrow could have implemented to improve its resilience, and it said that it really just hadn't progressed those ideas in any meaningful way, which is why they were left with this 10 to 12 hours of re-engineering that they had to do at the time. So I think that there's an important lesson for Heathrow here, which is, don't just focus on what's happening in your own market. Aviation is a global industry. The US airports all caught on to the impact of the Atlanta incident, which was extremely similar to what happened here. And they put in place sort of sensible mitigation strategies so that if they did lose power, they wouldn't lose service. And unfortunately, Heathrow didn't learn those lessons. So I think that we've got quite a lot to take away from this situation. I don't think we've heard the last of it. I think there's going to be further discussions, particularly around the relationship between critical infrastructure and their service providers, and also the relationship between the regulators and all of these different entities, whether that's the Civil Aviation Authority's regulation of Heathrow Airport or Ofgem's regulation of the electricity networks. So I hope you found that interesting. Please let me know your thoughts in the comments. Thanks.